Okay, perfect.
Great.
Okay, so this is the beginning of my presentation on space and logic. I'm trying to, I guess, like bring out and I guess make them appear, right? The relations between topology and logic, which we've seen like a lot about in a lot of the things we've been talking about, how, especially in Badiou, in like things with the transcendental and the transcendental logic, is all because really like that space is really it's basically a topology, but it's also characterizing like certain uh, like predicates and sets and things like that. So hopefully we'll get a little bit of the connections. The pictures here, these are just pictures I found on the internet. This one on the top left shows actually filters and ultra filters. So if you look at, so just to get a little bit of a, I guess, intuition, the ultra filter is going to be this whole thing with the light green and the dark green together. So what that is, that's it's a set, it's a large set, so it's a subset you see of the power set. So right, this whole set's 1, 2, 3, 4. It's a subset of the power set that is in the way Badiou explains it, at least he characterizes it as sort of like large sets, where largest is a sort of choice between like yes or no. So in the ultra filter case, the thing that's special about it is that either the complement or the set itself is always in there. So in a way, it sort of forces the law of the excluded middle when we think of this as a logic. A filter, on the other hand, is weaker, right? And a filter we'll see is a really good tool for kind of generalizing the idea of sequences. Which sequences we know like the convergent spaces, but the filter is sort of like something that converges everywhere. It hits every neighborhood of wherever it's converging to. And the thing on the right is actually, if we've talked about like manifolds or anything, if you ever hear the term atlas, that's what this is, but it's also an example. Something we'll be talking about a lot is sheaves, which are certain constructions on the space, right? That respect the internal logic of the space. Okay, let's just start going. Oh, how do I get to the next page? Oh, there you go. Here, okay. So here's a little background. Oh, I'm going back. A little background. I just can't see my mouse. A little background on some set theory and foundations of math, because first I'm going to talk about some category theory, but this is sort of a context for that, right? So since basically Russell's paradox, which I'm sure we all know, there's been a big, right, in set theory, they always kind of try to find like the right axioms. For a long time, there was like a big debate about what the right axioms were. One of the best examples of this is the axiom of choice, right? Which is basically saying if I have a collection of things, I can choose one thing from each thing. Turns out in mathematics, it's a very controversial statement, but also a very useful one. So mathematicians were kind of split because, for example, on one hand, if you accept the axiom of choice, you have something like the Banach-Tarski paradox, right? Which is when you take a sphere and you can cut it into subsets. These subsets are weird and infinite, but you're cutting it into subsets. You rearrange these subsets in some way, and then you get two spheres. So it's almost like creating something from nothing by cutting sufficiently dense subsets in something. So that's one thing that the axiom of choice implies, but it also implies some really nice things like every vector space having a basis, which is an incredibly useful thing. There's a few others. It's slightly more powerful, stronger than the ultra filter theorem, which we'll probably get to next time. Yeah, so in mathematics for a long time, they were trying to find like I guess the right axioms. What is like the one mathematics to rule them all, in a way, right? And then Gödel came around, as also probably some of us know, and he has two incompleteness theorems. The first one, which says that any consistent theory, right, which is capable of piano arithmetic. So piano arithmetic are the axioms that allow you basically to do the most basic arithmetic, to have a number and have a successor. And you can add, and then you can also subtract if you want. You can define more things on it, but that's the minimum is required. He showed that any consistent theory that is capable of piano arithmetic is incomplete, meaning that there are well-formed statements in the language, right, which have a meaning that makes sense. They're not just like gibberish, but they cannot be proven true or false within the system. So they're independent from the system. The example, the very, very famous example of this is the continuum hypothesis, which everyone talks about, which is trying to structure the size of the real numbers, which is the continuum with respect to the natural numbers. Okay, so the first incompleteness theorem says that anything is going to be incomplete if it has piano arithmetic, if it's consistent, right? The second one is this moreover. Moreover, any theory cannot prove its own consistency. So this is even worse. So it's saying that we can never know if the system we're using does not have an internal contradiction, basically until we find one. We can hope that it doesn't have one, but we can never really know. So this was, for a lot of people, was a big issue. I still think for some people still is an issue. But there was, I think, like a little bit of a change in attitude towards a more categorical mindset, that rather than accepting sort of like the one mathematics, there become many mathematics, right? So then there become many categories in which mathematics can be done, and each one has different rules, and many of them are probably consistent as far as we can tell. And there are different reasons for using each one, but there's no individual one which is really preferred. Yes, it's the same thing in the third point, that the continuum hypothesis being independent from ZFC, meaning that both there are models of ZFC. You guys all know ZFC. It's the, yeah, right, or from Badiou, I'm assuming.
Kentucky Fried Chicken.
Kentucky Fried Chicken. Kentucky Fried Chicken. But it showed, right, that the independence of the continuum hypothesis, which I really want to emphasize, was like a very important proposition theorem. It was one of the Hilbert problems from the early 20th century that he posted to be like one of the greatest mathematical problems if you could solve it. Turns out it's impossible to solve in ZFC without just deciding it on its own. So the conclusion is that you could never have, right, an exhaustive list of axioms that will basically let you do whatever you want to do with mathematics, because you'll always eventually somehow run into one of these sort of like incomplete statements, something that's independent. Right, so then on the bottom, the more modern interpretation, which first kind of category theory gave some hints, but then really topos theory, which we'll mention a little bit, which suggests that there's, right, as I said, there's a multitude of mathematical worlds. And really the idea is about, I guess, learning how to live inside each one, right?
And there's also the like categories of categories too, right?
Yes.
So you have this kind of meta leveling of.
Yeah, I think I actually have something about that. It's on the next page. How do I? There you go. Okay, so I have a little brief history of category theory just to give a perspective. But so it started in 1945 with Allenberg and MacLean in this paper, General Theory of Natural Equivalences, right? This introduced probably a lot of the notions of category theory that you probably have, many of you have already heard of, categories, functors, natural transformations, limits, and colimits, which are still sort of like the founding of category theory today. But they were really at that point more used as an explanatory tool for algebraic topology, where there's a lot of, where you often have a manifold, which is some continuous space, and you have different structures on it, like a homology group, which can give you, for example, certain like dimensional holes, or a homotopy group, which is another group on the surface. So it's this type of functor that gives you from a surface to a group. Homotopy has to do with curves on the surface and how they collapse, or if they do not or not. So at the beginning, it was more of an explanatory tool. You could draw these nice diagrams, which made kind of understanding the algebra very nice, but it didn't, I guess, like the philosophy of what category theory was about didn't quite click yet. Grothendieck, about 10 years later, in 1957, introduced sheaves, which, as we'll see, are incredibly powerful, which, in the way that he did it, right, he was looking at sheaves, which were these homological morphisms, these things that take like a surface or a space and give you some kind of algebraic structure. So the thing is that when he generalized it in this language of sheaves, it became kind of obvious how to apply the same tool, which is homology, looking at like holes, to algebraic geometry, which studies basically solutions to equations, which gets very complicated because these solutions themselves are these like strange spaces with weird geometries. So this is kind of the beginning of this like categorification, which is a process that, like, a word that mathematicians often actually use, where you kind of take a field of math that was already kind of developed on its own, and you see what it looks like in the categorical language. And very often what happens is that it turns out that structures that you had in this one place are the exact same structures you're using somewhere else. So it's very, I guess, like the language is very well suited for generalizations in terms of the logic of the overall space, right? Which is something we're interested in. And then later, throughout the 60s, Lavre, I don't really know how to pronounce his name correctly. He has a French name, but he's American. I think he's Southern. But he took this even farther, showing that category theory can be generalized for certain kinds of categories, especially what we call these Cartesian closed categories, which are categories that admit basically many limits and colimits. The limits and colimits are either gathering things up or sort of reducing things down. Colimits are usually gluing many objects together. Limits are usually picking elements from each object according to a certain constraint. I think I have that later somewhere. But Lavre, what he really did, he brought, I guess, like category theory to the fore in terms of potential like foundations of mathematics, where this idea of a topos, which is a category that's large enough that it has enough structure that it becomes sort of a nice place to do math. What we really mean by that is that it has many of these limits and colimits, because what these limits and colimits really correspond to are basically all the constructions that you do in the space. Like products of spaces are limits of the two, a product is a limit of a 2-point diagram. A pullback is a limit of a one object diagram. And you have similar things in everywhere, where you have all these very similar structures are basically everywhere. Also, toposes, topoi, however you want to say them, are also in a way generalized topological spaces, which we'll get to. which is already sort of another hint between logic and topology. Lauver also really emphasized the importance of adjunctions, which we won't go into deep today, but adjunctions are a way to understand an equivalence between categories that's only what they call equivalent up to natural isomorphism. What that really means is that it's, you could take the naive idea of an isomorphism between categories, which is just the categories look exactly the same as they are. But isomorphisms between categories are pretty rare. But if you weaken it slightly and make this a junction, where rather than them being exactly isomorphic, they can be isomorphic up to a certain natural transformation. And in this way, that you get these adjunctions, which are pairs of categories which are sort of like almost the same. And it's, many people say it's one of the most powerful tools, single tools in category theory, although, as I said, we won't get too much. Okay, and then basically since then, the same stuff has been applied to essentially everything. So almost every field of math now has some sort of like categorification where you can look at it in this context of category theory. And many places have, I guess, understood new connections based on that. Okay, category theory for philosophers. Why are some reasons that you all should care about this? So one thing, right? It's how I like to think about it is as a de-ontolization of concepts, right? I don't know if you guys watched that video I sent, which is quite good.
It's really good, man. The amount of stuff he clarifies in 6 minutes.
In like 6 minutes. Yeah, but he talks about how category theory is context rich and content poor. So I think especially in the context of Badiou, who talks about like set theory as ontology, I think it's a good way to think about this, right? A category, if you're looking at something from the categorical perspective, you're sort of taking a step back. You're not looking at the internal structure of it, but you're looking at its relations with outside things. And this is going to become very important when we talk about the Yoneda lemma, especially. So here, right, we look at their context over their content. So then they're understood with relations. Categorical approach lends itself well to universal constructions. So this is what limits and co-limits are. I have made a little picture. Oh, I went back. I made a little picture here. You can see, I don't know, I have to move this away. There you go. So the top point, right? So this D in the center, this is just representing any diagram. So what a diagram is showing a certain set of relations, whatever you have. It's really, in itself, is a functor from that diagram into whatever category, from really just like a graph to the category itself or to a set. Basically everything can be reformulated in terms of functors, right? But we say a limit of a diagram is a place that sees everything of the diagram. This is an way of putting it. So there is basically a projection from the limit onto every element of the diagram, such that if you have any other object that has the same thing, right? So really these don't have to be 2 arrows. They can be however many arrows. You get 1 arrow to each object of the diagram. But if you have another object, right, that has the same thing where it has an arrow to each one, we call these cones, these little triangles here. There's going to be a unique morphism from C, this other one, to the limit. So this, in the sense that I'm calling this a universal construction. It's saying that this object, this cone, which is the limit, is sort of the closest one to the diagram, in the sense that it factors through every single other cone that is also on the diagram. Okay, does that make sense? A co-limit is, of course, we see is the opposite. So you can imagine a co-limit. What it does is it takes each element from this diagram. So if we imagine the diagram is 2 points, the colimit of that is just going to be the disjoint union of those 2 points, right? The limit of that is going to be the product. So the union is you're putting together, the product is you're taking like slices, but not all limits are products. So categories in general, we say they're more or less similar, right? To the extent that they admit different universal constructions. So this is like the term I used before, Cartesian closed category, right? Is a limit, is a category that has all limits and all, colimits and small limits, I believe. And by like the amount of these universal constructions that exists, that actually often characterizes what space you're working in, right? So for example, you could say I'm working in such and such space because I'm able to take certain products or take certain quotients of things. So that all has to do with existence of different of these universal constructions, which are cones over diagrams. Yeah, this last thing is the same, basically what I was saying before about how you can use this to compare, right, different contexts by looking at sort of their internal algebra. That's really what category theory is all about. It's all about the internal algebra of contexts. Okay. Oh, there you go. Okay, let's get into a little bit of meat. So a functor, let's redefine this. A functor is we can think of it as a morphism between categories, right? So a category is made up of objects and morphisms, and the morphism between categories is a functor. So what does that mean? It means that you map every object of the domain C to an object of the domain of the codomain D, such that each morphism, right, is respected. So, and we also send the morphisms. So it's so each morphism from an object X to an object Y in the category C corresponds to a morphism f of f from f of x to f of y, okay? Such that there's two conditions. One is that if we apply it to two functions, right, then the composition of the function, it respects composition. So the composition goes in, as we see. So f of g composed with f of f is going to be f of gf. And also it's going to take the identity to the identity on whatever object. So this is the definition of a covariant functor. A contravariant functor is really this, essentially the same thing, but you just flip around the direction of the arrows. So a contravariant functor flips arrows. As we see, topology is kind of rife with contravariant functors. They're sort of like the basis of everything in topology. But we'll get to that soon. And then finally, a natural transformation, this is important, is a morphism between functors. Okay, so we're thinking of basically everything as a functor in the sense that our objects and structures on whatever base category we're dealing with are going to be defined as functors on that category that add something to it and add some additional structure. We'll see reasons why we can say that in a few slides. But a natural transformation, right? So if we can think of functors as a sort of object in themselves, then we want to understand what it means to translate from one to the other. Okay, so natural transformation is when we have two functors going in the same direction, from C, from some category C to a category D. The natural transformation consists of a morphism, right? For every X and C. So really what it is, the natural transformation takes in values of C and gives you a function that changes from fx to gx on that point. And we can see it's really what allows this square here to commute. So the natural transformation is what we get from some structure, right? Think of F as a structure on a space. Imagine we have a space G. We have two different structures on it. One is F and one is G. The natural transformation is the way that we translate between these structures. And it's sort of, when we say it's a natural transformation, it should make sense why it's called natural, right? The square, does anyone like not understand why, I guess this square looks the way it is? It's sort of, a lot of things in category theory, they often say things are natural in the sense that like there's a natural transformation that canonically has a certain property. So yeah, I don't know. Does this make sense? Any questions here?
I mean, yeah, the
Yeah,
notion of naturality is, it is a bit like, it just seems like it's more based on experienced mathematicians' intuition rather than like an explicit definition, right? Like I've never seen definition.
So I don't know if I'll be able to give a good answer to this, but it is not just a like whatever they choose to call natural. Usually naturality comes from having certain relations that are required to be there for whatever reason. Often this can come from the Yoneda lemma. I actually wonder if I look it up. I think I have to exit out of this to do that. That's okay. Let me quickly, give me 1 second. I want to search this now that we're on this.
Yeah, one way I like to imagine the natural transformation, at least, is like two pictures of a category within another category, and then the natural transformation is how you would change one of those pictures to the other picture, right? Just, I mean, it's another way of saying exactly what you were saying. And so like F would be a picture. If you imagine like your face, let's say, is a category, and then a river, or let's say like a body of water, is another category, then the reflection of your face in that body of water would be like F. But then another, let's say, reflection of your face, also your face, on that body of water, maybe at a different moment in time, would be G. And then the natural transformation is how it would describe how you would turn the first picture into the second picture, or the first reflection into the second one. That's like a metaphoric way, but yeah.
Yeah, so I just looked a little about naturality. I can go into this later. If I can give it like a good deep dive, but it seems like the idea of naturality usually comes about when it sort of seems like there are many constructions you can make, but for whatever reason, and usually there's categorical reasons, there's generally like only one really good choice, and there's a good reason to think. This is also sounds sketchy, but there's a good reason to think that is the choice you should make. Maybe that seems unmotivated and I guess arbitrary, but when you work with these things, a lot of things end up becoming natural. But yeah, we'll see. Okay, so in general, you have functors, which we're thinking of as structures on a space. And then we have natural transformations, which change between these structures. Oh, wrong way.
Sorry, can you go back to the natural transformation diagram? So if we want to read this diagram, X and Y are elements within the category C.
Yes. Well, y is going to be an element of the. Yeah. They're both elements of C. Yes.
And there is a function. There is a morphism between x and y, which is little f.
Mm-hmm.
And there is a functor that takes little f to some other functor, so some other morphism, which is f of f. And there is a functor g of f, which also. And then the natural transformation is the eta.
Yes.
At the morphism between fx and gx and fy and gy. Is that right?
Yeah, I believe I actually have a typo. One of these should be n eta sub y. It should be the one that is on the right. It should be eta sub y. But the diagram is correct. The diagram is
eta sub y.
Yeah, but in this this equation above the diagram.
Oh yeah.
Yeah, I just realized that. The diagram is correct though.
The diagrams. And the diagram has to commute in order for eta to be a natural transformation.
Yeah, so that's the definition. It's when you have these two functors. So you see there's actually two etas here. There's the eta for the x and the eta for the y. So you're changing it at each point. You're changing it at x and you're changing it at y.
Right.
But yeah, the definition of a natural transformation, and there can be many natural transformations. The definition of a natural transformation is this way of going from a functor f to a functor g. And you see, like if we imagine that, right, we look at this top functor f, we see that what eta does on either side of it, it's pushing it down to the g.
Yeah.
And the commutativity really just means if you walk both ways around, it's the same. And that's what the equation is, just the commutativity.
And then that equation that says eta sub x of f is equal to.
Yeah, so maybe I should put some parentheses. Yeah. So big F and big G are both functors. So they're acting on these functions here. So big F is acting on F and big G is acting on F as well. And eta x is a post composition with the F, and then eta of y is a pre-composition, right?
Mm-hmm. I'm looking at looking on the right side of the right side of the equation. Is the right side of the equation correct?
Yeah, the right side is wrong. It should be eta y. I don't know if I can change it right now. That's what I said before. But the diagram is correct.
Okay. That's fine.
Oh, actually. Does it work? There, now it's right.
But shouldn't eta y come out of be the first term before G?
It should come.
That's the weird thing. The ordering is backwards, and for some weird historical reason, the arrow that goes first goes on the left, and the arrow that comes after that goes on the right. You know?
I see.
Oh, I put the eta x on the wrong side. It's actually the left side.
Yeah.
It's hard. That's why I like to look at the commutation squares, because it makes it clear what is going in what order. The equations always mess me up. Anyways, I'll fix that.
Yeah, I understand that the morphism is read from right to left as opposed to left to right.
Yeah. And it gets really confusing.
Yeah, I agree.
Yeah. Okay, so
so you will correct these before you send them out.
Yeah, I can do that.
Thank you.
Yep. Okay, so let's talk about a few properties of functors. So if we have a functor, right, f from C to D, and then we're going to look at, right, the set map. So what this notation here, the C of x comma y and this D of f of x comma fy, that is the set of morphisms in the category C between X and Y, right? So these are basically the set of functions or morphisms, or however you want to talk about them, in these two categories between these points, okay? So a functor is going to define for two objects, X and Y, it's going to be a map from the maps from X to Y to the maps from Fx to Fy in D, right? So what it does, all it does is it sends F to F of F, okay? If it's injective, this map, we call the functor faithful, okay? So when it's injective on functions or on morphisms, it's faithful. And when it's surjective on these morphisms, it's called full. So the reason why there's a different notation, different language than there is for functions for this is because this is not really the same as injection or surge, or you guys are familiar with injective and surjective, those terms, yeah. Shall I explain it? Injective is just a function that does not map that maps, or I guess a function that maps each point to a unique point in the domain, right? So there's no doubling up. And then a surjective function is one that hits everything in the domain.
Codomain.
Codomain, sorry. So here a functor, right? We call a functor faithful if it does this for all morphisms between two objects. We call it full if it does this, if it's a surjection. So fully faithful functors, they often call them embeddings. They're not exactly embeddings, right? Because two objects could still get mapped to this. Two objects in C could get mapped to the same object in D. Two different objects. That's okay, as long as their morphisms do not. So it's a way of embedding one category into another category, making certain things equivalent, making objects equivalent, but keeping all of the morphisms. A fully faithful functor will keep every single morphism, and there won't be any overlap between them. So in a way, since I mentioned in category theory, we think about everything in terms of its relation to other things. So whenever we have one of these fully faithful functors, we in a sense have an embedding of our category in another context, but in which the objects could be completely different. The objects could be simplified. So it's kind of pointing to how objects aren't really, right? They're not foundational, but it's the relations between them that are the important things. A functor, right, takes compositions to compositions and identities to identities. That's in the definition, meaning that it encodes invariance of isomorphism, I guess isomorphism classes within C, or isomorphisms of objects within C. So it shows you, because it preserves all of it preserves the function information, right? If it's injected, if it's fully faithful, it doesn't have to do that. It can collapse them together, but it gives you extra constraint. If it's not faithful, it can give you extra constraints on your set of morphisms, and it can also identify morphisms with one another. But the important thing right here is that functors take isomorphisms to isomorphisms, which means that a functor preserves whether two objects are the same or if they're not. So if we look at two objects in C, if they're the same, then if we send them to D through some functor, then they're also going to be the same there. I guess for anyone that hasn't, I guess, gone very deep into category theory and how isomorphisms are used within it, an isomorphism is meant to kind of generalize the notion of equality that is not just set-based equality. So it's not that there's any idea of membership and things belonging or intersections or anything like that, but it generalizes the idea that two objects are going to be the same based on their relations with one another. Based on their relations ended up being related to the identity.
In other words, can we say if two objects are isomorphic, they can replace each other in a diagram?
Yes, that's one that's one way of thinking of it. You don't want to always think of everything sort of just, I guess, like within the diagram, because really what a diagram is a certain functor of basically a graph into some category or into some context. But the idea is that since functors preserve sameness, the idea of isomorphism in category theory can be very loose. For example, in topology, the notion of isomorphism is homeomorphism, which is what people often say when they say that in topology, like a topologist can't tell the difference between the coffee mug and the donut. What they mean is that in the category top of topological spaces, two topological spaces are isomorphic if there's a homeomorphism between them, which is a continuous bijection where the inverse is also continuous. But for example, in set, right? In set, it's just exactly set membership is isomorphism. So then isomorphism is just bijection. But in tons of other categories, there's tons of other notions of isomorphism. Isomorphism is always something that's contextual. So it always depends on whatever context you're working in. Okay.
Is the faithful property related to the home set is like the numbers of morphisms, right, between two objects? So
yes,
it's preserving the size of the home set between.
Yeah, so it will preserve the size of the home set in the image.
Yeah.
What I mean by in the image, I mean it'll preserve it for all fx and fy, right? Because you might not hit all the points in the category D.
Yeah.
Yeah. But yeah, in the image of it, it will,
Okay. And this,
yeah.
when you say that functors take isomorphisms to isomorphisms, doesn't that assume you have isomorphism in your category, or?
Well, I mean, no, it doesn't, because it's if you have one, right? If you have, I mean, a category will always have isomorphisms in the sense that an object is always isomorphic to itself, right? That could be the extent of it, but very often it's not.
But in any case,
he's also
taking stuff that is not isomorphisms, right? So why say? I mean, it's taking everything that you have in a certain category.
Sure. What I mean by that sentence is that if you have an isomorphism between two things, so if you have two things that are isomorphic, if you plug them into this functor, which is some structure on it, wherever they end up, they will still be isomorphic.
Okay.
So it preserves it. Doesn't guarantee they exist or anything like that. But saying that sameness is preserved under a functor, which is a great property to have. Okay, here, this is the meat. This is the meat and potatoes of the category theory stuff today. Oh, I went back. The Yoneda lemma. Often it's called the most important result in category theory, probably true. This is what's called the contravariant version. There is also a covariant version, it's basically the same. So what it says, right, this is like the lemma that establishes once and for all that objects can be completely understood in terms of their morphisms. Okay, so let's see what it says. So for every object X and every contravariant functor, right? So we're gonna have an object and we're gonna have a structure on the object. The set of natural transformations from C blank x. So what this is a functor, a presheaf actually, that takes in a value of C, of the category C, and gives you all of the morphisms between C and X. So X is our special object that we're concerned about. We want to know about X. But Yoneda Lemma says that the set of natural transformations from this presheaf C blank X to F is isomorphic to Fx. So what this means is that when we have a functor, if we want to understand the image of a category under that functor, it's enough to know all of the relations, which are in this case, right, the natural transformations from this presheaf to which we'll get into presheafs in a bit, to the functor, right? Because these are both functors. So it's a natural transformation. And this is the sense in which things are called natural, where you take one of the senses, all of the things, all of the arrows, right? I'm plugging in a number, I'm getting all the arrows between that set or that object and X. I'm taking the natural transformations from that to the functor. So what it says is that they're isomorphic. So that means an easy way to see this, right, is if we plug in for F some other object Y. Okay, so look at what happens. We have the natural transformations between the functor, which gives all of the arrows to X, to the functor that gives all the arrows to Y, is isomorphic to the set of arrows between them. So what this is saying is that imagine if I have two objects, if I want to understand how these objects relate, it's enough to look at this object, look at how it relates to everything outside, look at this object to how it relates to everything outside, and look at natural transformations between these two things. So this is incredibly powerful because it gives a connection between between objects and relations. An object can be fully determined by its relations, and we'll get to why that is in a second. But for now, all it's saying is this kind of confusing statement. I'll admit it's a confusing statement, which is saying the image of the functor is isomorphic to these natural transformations, right, which are functor maps. So it's saying that objects are isomorphic to morphisms of functors, which is weird already. So it's already like 2 levels above of natural transformations from the presheaf to X to whatever functor we're thinking of. Since this up here, okay, so if we go back to this second line, since it's an isomorphism between the natural transformations between the two objects and the arrows between those two objects themselves, this isomorphism, it's an isomorphism, this embedding is the embedding of the category itself into this category of presheaves, right? That each object can be thought of literally as the contravariant functor, which is where you just have a blank space, put something in, and you get the elements, the morphisms between that thing and X. This is called the Yoneda embedding. So what this is saying is understanding the object X is equivalent to understanding arrows that go into it. That's what this is. The C of this dash comma X is a functor, right? So it takes in an element of the category and gives out a bunch of morphisms. So this is what they're saying. There's an isomorphism between these, meaning that it's basically this contravariant functor, this presheaf, is basically the object itself. And in fact, we get an embedding of an object into its category of presheafs, which we'll get to ends up being basically all the structures that we can build on that set. Yeah, so it means that we can understand things by the morphisms into them, and there's an equivalent covariant version. So the covariant version says the exact same thing. It's just instead of having arrows into X, it's arrows coming out of X. Okay, are there any questions?
Yeah.
Sure there are. Yes.
Go ahead.
Oh, okay.
No, sorry, I had a question. I thought that somebody
Oh,
else.
yeah?
So you probably answered my question, but
Yeah.
in the first form, which is the natural transformation of
Yeah.
two things. One is a
Yes.
presheaf of a covariant function, and one is a functor itself, right?
Yeah, well, they're both functors. A presheaf is a functor. Did I define
Okay.
presheafs yet?
Yeah.
Oh, I don't think I did. I'm
No.
defining things in bad order, so sorry about that,
Yeah.
but we'll get to it.
Okay. So when we say the natural transformation, so
Yes.
they are the natural transformation of two functors.
Yeah. So it's not the natural transformation, it's the set of natural transformations.
Natural transformations.
So it's all natural transformations between this functor, right? Which is defined only on X. Really, what you want to think of this functor as is
But didn't you say that
yeah.
if we write C of X and Y, we mean all the morphism between X and Y in category C?
Yes.
So how?
So yeah.
Okay. So how is it a functor then?
Yeah. So it's a functor because there's a blank spot, right?
Okay.
In here. The blank spot is where we take in an object of the category. Okay? So it takes in an object of the category, it spits out a set
of morphisms.
A set of morphisms, yeah. And similarly, you can show that if you have two objects, if two morphisms, it's also going to work in the same nice way.
So I guess my first problem is how C of a blank comma X is a functor, not just a set of morphisms.
Yeah. It's a functor because it sends each element of the category. Maybe can I write on here?
Yeah.
Do that again. Oh, my mouse disappeared though, so maybe that won't work. 1 minute.
You got to get this X journal thingy.
Oh no.
I think if you go out of full screen.
Oh yeah, I was in full screen. Oh, here, annotate. Come back. There you go. Draw. Yeah. Okay, so if we have, so C, you guys can see this?
Yeah.
It's not going to be very thing. Ugh. From blank to X. Okay, so this is a functor from the category C to set.
Oh, I see. This is, in this sense, it's a functor.
Yes. Where each object, Y, right, is sent to C, Y. Oh, it's very difficult to write with this thing. Y.
Welcome to my world.
Yeah. I actually have this like tablet thing for drawing, but it doesn't work very much anymore.
Yeah, you write very well.
And then how does it act on morphisms? On morphisms, it's gonna send, I believe, F to something that sends C, where if F is from, I guess, X. Oh. Let me think. Yeah, I don't know what it does with morphisms off the top of my head, though it should just kind of come out of the definition.
So if f sends y to z, then this would send it to a c
Yeah.
z of cy
Say
of x
f
to c z of x, right?
from
Doesn't send
y.
f to that set?
Oh yeah, you're right. Yeah, you're right. It's going to be c. It's going to give a function from cy to z to, yeah, it's going to give us sort of a function between functions.
Yeah,
So
where the
c,
x is still.
uh,
I think the
sorry,
x is
this should be
simple.
x.
Yeah,
Yes,
exactly.
yes. Y, and here is going to be z to x. Yeah, that's right. So that's how it's a functor.
Yeah.
So it's giving for each object, it's giving a set because it's giving everything that's going into this object. If we do it the opposite, it's going to be doing all the morphisms that come out of the object. But turns out it's equivalent to look at either. I guess that's just clear. Okay.
Okay, now go back to,
Yeah.
So,
Oh, let me
this is the second
undraw.
page. Go to the previous page.
This one? Yeah.
So there is the natural transformation of two functors.
Yeah.
Is isomorphic to the functor of, so the right side, the f of x means how x is sent from category C to some other category.
Yes.
So f of x is an element.
Yeah.
And the left side is a set of all natural transformations. How could they be isomorphic?
This is, I mean, this is exactly kind of like the magic of category theory, right? There is no difference between an element and an arrow and a relation and a functor. They kind of all end up being the same thing often. Basically, everything ends up becoming a relation.
Right.
Essentially, nothing is internal, so it ends up working out. I'll let you believe me for that.
Okay.
Okay. Oh, why is it not going? There you go. Isn't that right? Yeah. Oh, I skipped a page. Here we go. Okay. So if we take this even farther, we have this isomorphism, which let's compare it to here. So this is now saying, right, that x, so this is really the punchline. Okay. I'm not going to go through the full details how we get to this, but using the Yoneda lemma, quick corollary is that x is isomorphic to y if and only if the objects, right, I guess the pre-sheaf of arrows coming into x is isomorphic to the one going into y, if and only if you have the ones coming out of them, right? So this really, right, Yoneda lemma kind of suggested it, but it was confusing because there's this natural transformation and there's image of the functor. There's all these weird things. When we apply it in a straightforward way, we get exactly this. The objects are completely determined by their relations. Does this make sense by this equation above, right? That if their relations in or out are the same, really that's what this pre-sheaf is. For any other object, you get its relations with that object, right? So if we know it for all of them, and if it's isomorphic for all of them, that's in the sense that it's the whole function is isomorphic. It's isomorphic to all of these individual ones, then the objects themselves are isomorphic, which is pretty great. So the Yoneda lemma actually motivates this focus on these things, pre-sheaves, which are functors, which are of the form here from F, from C-op to set. The whole C-op thing basically just means we're looking at arrows that go in, right? Or it's really what it does is it flips around the arrows. But we're only looking at arrows coming in, so the pre-sheaf is going to be a functor that does exactly what we did. That here, the c dash to x is going to be exactly the pre-sheaf. We can interpret them as more complex objects built out of simpler objects of C. This one that is, right, that is the pre-sheaf that is what we say generated by X is sort of exactly X, but in general, pre-sheaves can be generated. They don't have to be just in this form, which is one object. But in general, I believe there's a theorem that they actually, you know, don't quote me on this, but I believe there's a theorem that all pre-sheaves like break down as a product of these Yoneda embeddings.
Right.
So,
Maybe one thing we should think about is the difference between representable and non-representable pre-sheaves. Because this C one is a representable one, right?
Yeah. So the representable, non-representable pre-sheaf is exactly a representable pre-sheaf is just a pre-sheaf that is represented by something as a Yoneda embedding, right? I believe that's right. Which means that the pre-sheaf is essentially an object of the category already. Since we're saying that, right, that looking at arrows into X or arrows out of X is the same thing as looking at X itself. And then pre-sheaves that aren't of this form, that can be more complicated. We'll probably talk about a few sheaves and pre-sheaves. But the reason why pre-sheaves are sort of really nice is as I mentioned, the category of pre-sheaves admits all limits and co-limits, which means that it's very rich in structure. Pre-sheaves, they combine together well. We can basically always take limits and co-limits of diagrams of pre-sheaves, which becomes extremely useful when you want to construct things. So if we have a pre-sheaf, we're going to interpret fx as a set representing ways x occurs in f, right? So it's still it's a structure on top of this original object x, which gives it a new context. And then applying one of these to a function is interpreted as mapping each occurrence of y in f to a suboccurrence of x in f. So these functors are basically a way of changing contexts, or of adding structure, or of comparing different things. Basically, everything's a functor. They're great. Any questions on that?
Even regular morphisms are functors.
I mean, yeah, from the one object set. Like, for example, this is actually something I meant to add in. But you can interpret, right, points or like set, well, that's not what I was going to say, but set relation or points of a set as a functor from the one object category into them. All a functor from the one object category does is it picks out one thing. And it says that's the thing that I'm picking out. But you can do this the same thing where this kind of like categorification, where objects that seem to before either be imminent to whatever object it was, or I guess like sort of seem natural, often have a categorical interpretation, right? So like points are just inclusions of the one object category. A topological space, as we'll actually see, can also be interpreted as a type of morphism into the Sierpinski space, which is just the one is greater than 0 space of 2 points where this 1, 0, where we just choose open sets or non-open sets. And we'll actually see later a filter is also a sort of morphism to that space, but that is has some different properties. So looking kind of generally, we're not going to go too technical into this because it gets very difficult very fast, but I want to give kind of a general overview, an idea of what these things are. So categories of presheaves on a category admit colimits, all colimits. I guess I was mistaken saying they have all limits, but they have all colimits, which is essentially gluings together. So presheaves always glue together well, meaning it's a free co-completion of C. So basically, what a category of presheaves on a category C is, what it like really is we take all of the completions, all of the limit completions of that set. What I mean by that, let me maybe draw it a little bit. Get this back. So I mean, if I have a category here, imagine I have a category C, and it's going to live in this little bubble. I'm going to have, I don't know, I'm going to make it pretty simple. We're going to have a few points. Maybe there's a morphism here. Maybe there's another point just hanging out. Okay, so the category of presheaves, which we're going to write like this. So it's all of the presheaves from C op to set is going to be equivalent to the free co-completion of C. So we're going to take all colimits. So we're going to do this. Okay, that's a colimit of this diagram. This can be one thing that I'm going to gain. Well, there'll be a colimit, right, of like these things. Just be putting these together. There'll be one for, oh, I didn't mean to do that. Undo. There'll be one
You can like Control Z, yeah.
like for here, yeah. For here. So this is an ugly drawing, but the idea is that, right, if we have this category of presheaves, which we already saw by taking these representable presheaves, these are going to be the representable ones in here, inside the category itself. They're the points of the category. But then they also combine. So what taking a category of presheaves over a category does is it takes the category you already have and it adds these extra completions on top, is when we take all limits of whatever diagrams we have. As we said, these limit diagrams are basically gluings together. So we basically glue everything together in all ways that we possibly can.
Oh, that's interesting.
Yeah.
Is this at all similar to how in abstract algebra you have like an alphabet and you can create like is it a monoid, free monoid on the algebra such that you make all strings possible using that alphabet? So like, let's say the alphabet is like A, B, C, then the free co-completion would be like all strings of any length containing A, B, and C, right?
Would that be a free co-completion of it? Yeah, that is like the general construction of like a free group. It might be. Free in general just means that you're basically like adding like variables to something. Like for example, a really good example is the free what's it called when you adjoin an element? It's called the free product. Anyways, when you take like a ring or a field, which doesn't really matter what those are right now if you're not familiar, but you can adjoin an element and we just call it X, and then you get the ring or the field of all of the functions, right? Or all the polynomials in the language of that ring, but with X. So you move like from the base structure, add something, you get a bunch of other things. So it's a similar idea, yeah. That's really
like
word free. I don't know off the top of my head if there are co-completions though. I would have to think about it, but maybe. Yes, it is definitely similar. Let's create this. Okay, so if you take a pre-sheaf, right? A pre-sheaf, all it is, I guess I didn't define it before. A pre-sheaf, it's just definitionally is a functor from C-op to set. So all it does, that just means it's a contravariant functor to set. So it's going to flip the arrow when it happens. So adding 2 additional conditions, which I won't give rigorously, localization and gluing. Localization basically means that you can localize around points. So it's a topological sort of thing where I wanna get close to a point, and it has to be consistent at that point, and there has to be a unique one. And gluing is when they come together. When I'm gonna take a bunch of these different open sets, or whatever I want to call them, and I'm gonna and you glue them all together in a consistent way, such that the internal logic of it is preserved. So they agree on the intersections. This is something called a sheaf, which is basically a pre-sheaf that has a little bit of like extra topological flair, right? So it's they're what we call a category of sheaves on the site. This is what we call a Grothendieck topos, just a general thing. This is a this picture here is a picture from one of those other videos from the same guy on his introduction to toposes. I just thought it was a really nice picture, so I stole it. But the idea is that it's showing that if we have a category of sheaves on a site, we're not going to go too much into this. It's basically a generalization of a topological space, a place where you have ideas of covers and how to combine things together in the appropriate way. But a topos is going to be a nice place, as here, nice place to do math. What that means is you basically have all the internal logical structure you need to do all of the normal constructions that you do in basically every field of math, which generally end up being about taking these different limits and colimits. But what's nice is that when you look at this, like even you see this in this category, a lot of what happens now in topos theory isn't even so much like doing like foundations of math, trying to like find what like the most like basic or general thing is, but it's often kind of making these bridges between different worlds. So this is what this mathematician, me and Gabriel and Dennis talk about a lot. Olivia Caramello, who's has some good drama too.
Yes,
but
very cool gossip.
A lot of her work, yeah, a lot of good gossip, is based basically on bridging toposes together. Okay, that's enough of this category theory. I've had enough of it. Let me open this. Oh, I have to stop drawing. That's what I have to do. Okay, let's apply this to Bediou a little bit. So I guess the reason why this is structured is I guess applicable in his objective phenomenology, the transcendental, right, which is the space of appearing, is where the differences that make a difference appear, right, has a structure of a locale. A locale is basically has the structure of a topological space, right, where you have oh, I guess we'll get into topological spaces in a second. That has a structure of a topological space that's not required to have points. So it's not required to be based on a set origin. So then there's this whole thing of what you call point-free topology, where your open sets, right, could be literally have no like objective support for them. One way I like to think about this, maybe this is not a good way to think about it, is if you want to think about something that we can say, in a sense, exists, but also in an ontological sense, right, does not exist. For example, unicorns, right? Unicorns aren't, like, they don't exist. There are no actual unicorns, but they do exist in a sense. They exist, right, in literature or in the popular consciousness. And we could say that there's sort of like a locale that has this structure of maybe unicorns, which intersects many different things. It intersects pop culture and intersects many different things, but it has no singular point at the bottom, which is like the unicorn you're actually talking about, because they don't exist in the world. That's how I like to think about it. Maybe some.
I think a good way of talking about it that makes that clear is, let's say, the unicorn is a sort of abstraction from a bunch of text.
Yes.
Like, you don't get the actual unicorn below, but you do get to call parts of stuff that you can bring together under that name, right? Just to, I mean, there is no connection with this to fiction necessarily, especially because, but you actually ultimately will say that all atoms are real, meaning that there is something below them, even if it's not the thing that appears in the world, right? So there would never be a unicorn if there isn't something materially supporting the appearance of unicorns. But that doesn't mean that the support is a unicorn, right? So for example, I mean, you can have like a forest with a bunch of trees, and you can do like you can kind of cut out some leaves and call it like a region, but there is no one thing called that region in the world, right?
Yeah.
It's like
it's a fuzzy set, right?
It's a fuzzy thing, yeah.
Yeah. Anyways, this is a little bit of, like, I guess, the intuition of why something like a locale is even interesting. But right, it's an important point because the whole theory of points in Beiju is a totally separate thing that comes after the whole logic of the transcendental, because they're not actually guaranteed to always exist at sort of the basis of every one of these open sets. So this transcendental functor, which is really a sheaf, as we described before, right? It's going to assign these open sets of T. The open sets of T are regions of minimal difference, where each place, right? So for example, we could say in areas of the stairs, we can say in each one of these, like, little regions of the stairs, we can say it's part of the stairs. And in that sense, that they are equivalent in some sense, and they have minimal difference with one another. And there's this whole structure to it, right? So this is also another way that we can see how these sheaves are actually objects, right? For example, we say this, I don't actually know what it's called, this like gazebo-like thing is the whole thing, and it contains the stairs, and it contains also the center column, right? But these are all really sheaves, which are picking out sets from this painting and assigning certain predicates to them. And the predicates are something we choose, ultimately. And ultimately, right, the important thing is that the construction of this functor depends on the choice of scale for the world, which is the thing, right, we've been thinking about, which is a scale really is sort of whether the topology we're looking at is more coarse or more fine. There's I guess there's a rigorous way in which we can talk about that in terms of topologies actually being included in one another. And it also depends on the gluing compatibility conditions, which are local conditions of logic, essentially. This is a little quote from Dennis's paper. Shout out to Dennis. But there were a few, where he talked about the sheaf of prices. I just thought it'd be a good thing to go through. Where he said, we assume that the space of value is well understood, and we can join Hayek in celebrating the miracle of the price system. However, this if this space is non-trivial, then we cannot trust that a sheaf of prices exists. So I don't know, maybe Dennis wants to say something about this, but there's right, the idea that the market is sort of, right, like internally consistent, that there aren't these points of contradiction that will sort of explode and reveal the contradiction of the whole thing. Like this assumption that there's perfect competition is basically ensuring that there is this sheaf of price, the sheaf that gives to each region associates prices, and then that this sheaf is consistent and it locally agrees with everything. So then later he says that to sheds our ideas of convergences of prices, we have to do that and instead incorporate data generated by global crises, just saying that instead of just looking at only this local situation where I'm going to the store and I'm giving the guy money and I could leave if I wanted to sort of situation, we have to look at how sort of these like global, which are sort of topological crises that come into play. And all the way through to the end, he talks about how the topological factors, which are like the contradictions in the price system, are going to come down to singularities or points where the sheaf of prices breaks down. I don't know if Dennis wants to say, is he still here?
Yeah, actually, I would like to pretend like I know what I was saying here, but
sure.
The one thing I left out here in this quote actually is that in Marx already points out this. It's not only the global crises that prevents the sheaf from existing, but it's actually the existence of profit itself. Because I think like when Marx says like, you know, exchange wouldn't really happen if there wasn't this notion of like if you're just exchanging like for like, right, then there will be no like motivation for this market system to exist. The market system only exists because you can exchange for profit, right? So the movement from simple circulation to capital is already an obstacle in the sheafification process. So I think that's something to add here. I didn't really talk about that, or
would you interpret this sheafification as like the sort of like what's the word I'm looking for, the like whether the market like converges or not, or like I guess saying that local market conditions are going to converge, or always going to?
Yeah. One way is to say like, the supply and demand curves of different commodities will converge on a global scale. So like the price of corn globally is reflective of the conditions of supply and demand locally, of like corn in one region, corn in this other region, right? And the reasoning is that, okay, if there was not a convergence, then someone could make a profit by buying the corn low in one area and selling it for higher, right? So the fact that there's profit means that there's a motivation to make things consistent, right? And any price imbalance means someone can, there's a motivation to try to make it consistent, even though that's not what no capitalist is thinking. I want to make the market consistent. They're just chasing profit. But on the global scale, the consistency is the end effect. But then the problem is the fact that there is surplus value means that the workers don't get paid enough to actually buy the products that are produced in the end on the global scale. So that would be one generator, what I called in the paper a topological generator of crisis. It's topological in the sense that it's not to be found in any of the local pockets of the market, but it can only be thought of as like the way the markets are glued together, which I didn't really know how to go further than that. Like how can we think about gluing in or non-trivial kinds of gluing, because it's not very, it's not very clear to me actually what that means. Right. But yeah, that's what I would add.
Yeah, that's good. Okay, let's 1 sec. Let me just check. Okay, we're good. Let's go on to topology. That was good, Dennis, though. We'll get hopefully more into that stuff later next time. But now let's do some topology. Let's kind of give a general idea. This is gonna be a little more simple, I guess. So when we think about space, I guess the most important notion, right, is that of localization to a neighborhood. So space, what we're saying when there's a space, rather than just a set, which has no additional structure, a space for each point in the space, we need to know what it means to be like nearby that point. And this idea of nearness, and of neighborhood, and also eventually of predicates, right? Or choices of certain predicates is going to be an open set. And just the complement of an open set. So if the complement of a set is open, that set is closed. As I said, you can interpret them as predicates, where the intersection between the spaces are a place where both predicates are true. The union is a place where one predicate or the other predicate is true. So you can see how logic can come out of that. The implication to, if I remember off the top of my head, it's like the intersection with something is less than something else. It's in Badiou's book, if you're curious. But you can get implications too, so you can get the whole logical structure from this. So when a space has sort of many of these open sets, we're going to say it's a more fine-grained topology. And when it has less, it's going to be more coarse. But it's important to consider, right, that having something more fine-grained is not always better, right? Because the extreme of the fine-grained example is going to be where every single set is open, which is fine, which tells you absolutely nothing, right? So you have to choose certain things that you're focusing on, certain predicates or certain neighborhoods that make a difference. A more modern interpretation about spaces, which maybe we'll get into later another day, is there are places where you can put sheaves. So about our talk about how all objects can be seen as basically the sum of all their relations with other objects. And since a sheaf, right, has these topological properties, basically anything that admits a sheaf, we can think of as a space as well. But, oh, there you go. Here, okay. So topology, the definition of a topological space is gonna be a set along with a set of subsets, T, which is the topology, we call it. It is the set of open sets. It's always gonna contain the empty set and everything. So it has the top and bottom elements, and it's gonna be closed under arbitrary unions and finite intersections. So you should already, for anyone that read Badiou, recognize Heyting algebras, recognize the transcendental, exact same structure here. Just really quick, a sub-collection of sets also, we call it the basis. Basically, if it is contained, if for any x in the set, we can, it's contained in one point of the basis. And for any x in an intersection, we have something which is of an intersection of two things in the basis, we have another thing that is in the intersection. So a basis is just something that can produce a topology. when something is a basis for a topology, it's in the same way that a vector space basis is the basis for a topology. It can produce the whole topology just based on doing unions and intersections with the sets of the basis. A few examples. The trivial topology is no structure in the sense that the only predicates we care are the always true predicate and the always false one. The discrete topology is the opposite, where we look at the entire power set. And then the last example, so this is the entire power set. It's gonna be everything. Every single set is gonna be open, and also every single set is gonna be closed. So it loses its whole meaning. And if we have a metric is just a way of measuring distance. You also have a topology that's induced by that, it's induced by the basis of open balls with radius r around x, which is just this. It's just all the points which are less than distance r from that point. So it's gonna be generated by all of these such for any r and for any x. Does that make sense? Pretty simple. Okay, let's go through. We're going to go through pretty quickly, probably a few properties of topological spaces and things you can do with them. The first most important thing is continuity. We can say what it means for a function to be continuous. So the intuition for a continuous function is that there's sort of no jumps, but really what that means is that you're sort of staying within each open neighborhood. The important thing to realize about these is that the definition, right, is a function from x to y between topological spaces is continuous if you have for each open set in the codomain, the inverse image is open, right? So if you take anything in where you're going and you open set there, if you go back and it's still open, then it's a continuous function. The idea is that you're always going to be, no matter what choice of neighborhood in the codomain, you're always going to have an open set which is able to basically be inside of it, so that you can always, the idea is that if you move a little bit in a continuous function, in the image, it's only going to move a little bit. And this already hints to a really important topological functor, which is the forgetful functor on topological spaces, which what it does is it takes sets to themselves, and it takes these functions, a continuous function to a continuous function between the open, to these functions between the open sets that goes in the opposite direction. That's the way in which it's contravariant. Another property that you can define with topology is connectedness, whether a set is connected or disconnected. So it's connected if it can't be expressed as a union of two disjoint non-empty open sets. So if you cannot separate it by two open sets that don't intersect at all, or equivalently, which is a more categorical definition, is if every continuous function to the 0, 1 set is constant, where 0, 1 has a discrete topology. So what this means is that it's just a 2-point set, and it's saying that anytime I have a continuous function, that it's going to be constant. What that means is that because there's only two options, and there's the discrete topology on here, you cannot jump between 0 and 1 in anything that shares an open set, or anything that is sufficiently close to one another connected. So you see in this example down here, because they're disconnected, I could send this whole thing to 1, this oval, I could send the triangle to 1, and I could send this thing to 0. So it shows that it's not connected. But if it was connected, we couldn't do this in a continuous way. So if these were all one blob, everything would have to go to either 1 or to 0. Okay, Hausdorff spaces. A Hausdorff space is a space where each pair of points can be separated. by the topology. So it means basically that you have enough open sets such that any 2 points can be distinguished by an open set. So you can think of this as any 2 points can be distinguished by some predicate. So there aren't distinct things that I cannot tell the difference between, is one idea of thinking about a Hausdorff space. And if we add compactness later, it's going to become very important. We have one nice thing about Hausdorff spaces. They are closed under subspaces, products, coproducts, which means that if I take a subspace of a Hausdorff space, it's Hausdorff. Same thing with products, same thing with coproducts, but not the true for quotients. Quotients are basically, they are gluings by surjections. When we say that if anything is mapped to the same thing, then it's going to be the same point. So we're gluing the space together. So really the idea, and if you ever want to come up with a Hausdorff space, the easiest way is to glue it in such a way that there's 2 points that are distinct, but are contained in every single open set with each other. You could do this like by taking the real line, adding a point, which is glued to 0, but is distinct from it. And then you have a weird Hausdorff space that has 2 points sort of in 1 point. But there's a theorem, right, that every space X is the quotient of a Hausdorff space, which means a quotient, right, as I said, is like a folding. It's the sort of the opposite of this colimit. Every space is a quotient of 1, meaning that if I ever have a non-Hausdorff space, in some way I can unfold it and have a Hausdorff one, which is just a nice result to have. We're just going to go sort of quickly through these topological things. Let me know if you have any questions.
Wait, so I didn't understand that part about gluing a point to 0, but having it be distinct.
One second. Give me a, let me look it up. I believe it's called, maybe that was a bad example. I don't think off the top of my head. Let's actually think of a non-Hausdorff space.
Because just how I'm visualizing Hausdorff, it's like 2 points.
Oh, here, yeah.
And you
go.
Yeah, just Hausdorff means for any 2 points you have in the space, you can draw this like circle right around them, and actually that's what you said here, right? There are 2 disjoint open sets, U and B.
Okay. Yeah. So let me actually draw. So how you can do that, if you're curious, where's that draw here? If you take.
So that means that they are in that diagram. They belong to different open sets.
Yeah, you can find 2 open sets that are that they're different in. But they could also be one that they contains both, right? But it just happens to that at some point they split off into. Now this looks like a face, but yeah.
Yeah. So the idea of how you actually do this, so actually this is one of the main examples of a non-Hausdorff space, is if you take 2 copies of the real line. So I'm gonna have R, there's one here. I have another one. And I'm going to take a quotient of the union of them. Or of, I guess, not of the union, of the product of them, such that a point. Oh, sorry. Yeah. Oh, actually, no. Yeah, the union, the X, comma. We're going to call this RA and RB. X, comma A. We're going to make this equivalence relation is equivalent to this is really bad. X, comma B. Right. So they're equivalent if the X's are equal, and if there we go. X is non-zero. Okay, so what we do, this is the equivalence relation. So we're going to say these two are the same things, and we're going to mod out, we're going to quotient by that. So we're going to take, so I don't know if you guys know what a quotient. A quotient is when you glue things together. So we're going to have RA, disjoint union with this R sub B. Oh, that's a bad one. We read it like this, quotient, whatever this relation is. It's going to say each one of these points are going to be the same point unless they are 0, which are going to be distinct. So there's going to be 0A, and there's going to be 0B. And this is a well-defined topological space that inherits the topology from there's something called the quotient topology, which is how you can induce a topology based on these quotient relations. And yeah, this ends up being a space which looks like this. It looks like the real numbers, and it has an origin here, and it has an extra point here. But this one is kind of connected to here because this point, right? These points are separate, but this one on top is actually contained, right, in this open set here. It contains both of them, so it's very strange.
So
this is a non-Hausdorff.
Non-Hausdorff, okay.
Yeah, around this one point, yeah. So you could have actually even more complicated non-Hausdorff spaces. A good example actually from this book, what's it called? Like the Fearsley space or something like that, which is the space, which is when you let a set be open when its complement is finite. So you basically get all of these in like a big space, all these infinite sets that just have a few sets missing. And if you have all these infinite sets, you cannot tear them apart from one another, basically ever, no matter how hard you try. Yeah, so that's a bit about Hausdorff spaces. The idea of points is kind of like not fundamental, I guess. It's one way of thinking. Oh, I keep forgetting to deselect my thing. Okay.
Yeah, actually, that's another question I had. So when you move from these spaces with points to spaces without points, what happens to all these like separation type things? Like, it doesn't really make sense to call a locale Hausdorff, right? Or does it still make sense?
I mean, you could call it Hausdorff with respect to the points it does have. Yeah, I guess.
Okay, so you would still need to give it some points at some point.
Yeah, but locales have no points. Yeah, because the definition of Hausdorff has to do with points. It has to do with it has to do with like when a space is not Hausdorff in the place where points cannot be, I guess, uniquely localized. There's no way to like zoom in so far that you know specifically what point you're talking about. Even if like you take sequences of these open sets. Oh, okay, this is the big one. Compactness, which took me in like undergraduate analysis so long to understand. But it's really not that bad. The idea, right? Okay, so there's this abstract definition of it, which is saying that anytime, if you have a space, it's compact. If any one of these open covers always has a finite subcover. So an open cover and just a family of open sets that covers, if the union covers the whole thing. Okay, so let me draw. Oh, I have to get out of this thing. So imagine if I have a space. Oh, I'm moving things around. Draw. Imagine if I have space X here. Then an open. Let me switch colors. Can I do that? Yeah. Okay. An open cover is gonna be a bunch of open sets like this. That together they cover the whole thing. Okay, so we can see this as compact. So the term compact is suggestive that it's not exactly that the space is small, but it's that the space it is small enough like for limit points, in the sense that the really important thing about compactness is that every convergent, how it's used in analysis a lot, is every convergent sequence has a limit that's inside the set. So if you have one of these compact sets, you can't escape the set by taking limits. And that's important. Compactness is also related to model theory, which hopefully I'll be able to talk about next time, where the compactness theorems are basically saying that a theory can be broken down to a finite number of statements. That you don't need an infinite number of propositions to describe that theory. So it's a similar thing that you can, anytime you have an open subcover, so these can be infinite, that's the whole idea. So if there's an infinite cover, it's compact if every single time you can take a finite subcover. So compactness has some good theorems here, right? So we say so it works sort of the opposite way that open sets do. Remember, open sets, it's the inverse image. So if you go backwards from an open set, it's going to be open. Compactness works the other way around. You can push it forward. So if the space X is compact and you have a function between the two, then the image of X is also going to be compact. You can push it forward.
And so
yeah.
compact question, can you have a space that's not connected but is compact?
It's yes.
Okay.
Yeah, so compactness, we'll see actually down here, the Heine-Borel theorem, this is a big one, in Rn. So if you're working in the, I guess, like Euclidean space, or the real numbers to some n, a subset of Rn is going to be compact if and only if it's closed and bounded. So closed, right, is the complement is going to be open, but the idea of closed is like it includes its boundaries, I suppose, if you think about it in terms of Rn. So compactness is equivalent to being closed and bounded in Rn. Bounded just means it doesn't go off to infinity, the set. So you can, somewhere you can put it inside of something. Yeah, compactness works well with limit points. Limit points are, we say that a point is a limit point if every neighborhood of X contains a point not X, but in the original set. So it's something like this. So we see limit points can be like a boundary is a limit point, because any open set, if I go around it, this open set's always going to have something inside. Anything inside is a limit point, okay? Because if it's in the interior, because I can always take sets smaller. But something that's not going to be a limit point is going to be if I have an open set. Dotted lines are hard. Imagine if I have an open set here. Actually, no, that will be a limit point. What will not be a limit point will be if I have a point like out here somewhere, just by itself. This point itself is compact, but it's not a limit point, because if we take an open set with it, it doesn't contain anything else. So it means that a limit point is the idea is that if you have a sequence in that space, it can approach it. Balzano-Weierstrass is a big important theorem in the theory, I guess, of compact sets. That this way of phrasing it is they're saying every infinite set in a compact space has a limit point. It's not saying that it converges, so it doesn't have to be like at the end, but it's saying one of the points in it is going to have to be a limit point. An equivalent way of thinking of the Balzano-Weierstrass theorem is that every bounded sequence has a convergent subsequence. The sequences stuff we're not going too deep into because filters are better. Okay, we're getting close to the end. Okay. Now there's this notion of first countable spaces. Oh, whoops. So a first countable space is a space where each point has a countable neighborhood base. What that means is that the basis, so it's going to be a neighborhood base is really just, it's going to be a basis for a point. So it's going to say, I keep moving you guys, 1 second. So first countable space is one in which for every x and x, you have that every open set containing it has a member of this neighborhood base, which is contained in that open set. Okay, so everything, it's always going to be able to kind of filter something smaller from any open set. And that these basis is countable. The idea of first countable is basically that since it has a countable basis, it's going to work extremely well with sequences. And in fact, first countable spaces are going to basically be able to be completely characterized by how sequences act on them. We'll see that this is not the case in general. And if we want to do this in general, we have to actually go instead of from sequences to filters, which we'll touch on just at the end. It's second countable if it has a countable basis for the whole thing. That's not going to be super important right now. I just thought I should add it in. So this theorem, this first one, is if we have a first countable space, then being Hausdorff is equivalent to each sequence having exactly one limit. So that's really useful. It's saying anytime I have a sequence, if that sequence converges, it converges to one thing, right? So something not like in the case of that line with 2 points, you can't approach 0 because then it's going to approach both of them. Mm-hmm. So in the first countable space, Hausdorffness, oh, I'm moving stuff around, whether points can be separated is completely characterized by sequences. Similarly, if you have 2 first countable spaces and a function between them, this function is continuous if and only if, as you expected, every convergent sequence which converges to some point x, the sequence where you apply f is going to approach the f of x. Whatever the thing was approach. So this is just showing ways that we can characterize spaces, right? So really, we don't want to do this just in first countable spaces. We don't know, we know we have a topological space and the kinds of things we're thinking about. We don't know if we have any of these kinds of properties, which in like traditional mathematics, almost everything is the first countable space. And generally, you don't have to worry about this. But because we are working in a more general framework where basically the only restriction, or for example, space of appearing is this Heyting algebra structure, which is the topological stuff. So something like first or second countable is not something we want to keep, which is why what motivates the definition of a filter. So filter is going to be a downward directed, non-empty, and upward closed poset on the power set. What this means is that if I have anything, the upward closed means that it's always going to contain larger sets if I have something. So it goes all the way up. So this is in the sense that Badiou talks about it as being large sets. It's downward directed in the sense that if I have 2 sets, which we're going to call large sets, they should also intersect at a large set. And of course, the whole thing shouldn't be empty. We're going to talk about proper filters. Proper filter is just a filter that's not the whole thing, such that there's something that's not in it, in the set that's over. An equivalent definition of a filter, which is sort of similar, right, in spirit to this alternative definition of connectedness is a monotone function from the power set, right? The power set is 2 to the power of x, just all functions 2 to 2, where it's the Sierpinski space. Meaning that all of the elements of the filter are going to get mapped to 1, and everything basically below it is going to get mapped to 0. And these are also known as meet semi-lattice homomorphisms in order theory, because they come up in studying posets in general as well. But this is also the way to characterize a filter. We're not getting into ultra filters today, but next week. Yeah, I think that's everything I want to say here. Yeah, once again here, you see this is a filter. It's upward closed, downward directed. You have these two, you get the intersection, and it's not empty. And it's a proper filter. Finally, let's get to the good stuff. So I have a few nice theorems about filters, which is generalizing the stuff we were talking about before. So the idea of a filter, right? So actually, wait, let's go back to this picture. You can see in this picture of the space that the filter actually, it converges to a point. And there's a notion of convergence for a filter. This notion is, if you have, I believe I have it here. Yeah, filter F converges to a point if and only if it contains every neighborhood of that point. So the idea is that every neighborhood of the point is gonna be somewhere in here. So I can go all the way down and go as close to the point as you want, and that's still gonna be in the filter. And that's gonna be the notion of converging to the filter. So this is in the way, because it's upward closed, right? We're getting everything that contains it. Then the filter is sort of converging like from many places at once, because it's many sets that are nested into one another in different ways. And if they converge around one point like this, we're going to say it converges in the same way that we say a sequence converges. If we go far enough in the sequence that things match up. So 3 theorems we have. First of all, we can completely characterize Hausdorff spaces by limits of filters. So a space is Hausdorff if and only if is and only if and only if limits of convergent proper filters are unique. Okay, I'll repeat that. It's Hausdorff if and only if limits of convergent proper filters are unique. So proper means it's not the whole thing. Convergent means it contains every neighborhood. The filter is a filter. So that's nice. That's completely amazing. Characterizes Hausdorff space. Yeah. Another one, if we have X, a space with a subset A, we can actually know if A is in the interior or not. Of the closure. A space is, we're going to say it's in the closure if and only if there exists a proper filter containing A that converges to X. The idea, right, a closure, I'll draw this, is if we have an open set kind of thing. Oh, this is terrible. But maybe like on one side here, it can be closed, right? The closure is just, we're just gonna close it off here. It's taking, the closure is by unioning all the limit points. It's gonna be the space plus its limit points is the closure. So we said that the closure can be something could be determined in the closure if filters converge to. And finally, we can say the big one, that a function from X to Y is continuous if and only if every filter, for every filter F and X, if it approaches a small point X, then this pullback of F of the filter along F approaches F applied to X. This is another way that we can characterize completely. So it generalizes, it uses a more general notion called filters, rather than sequences, which is the traditional way to do all this stuff, and generally how it's taught in analysis. But filters generalize it. They generalize it to all topological spaces. You know, nothing has to be first countable or anything like that. Yeah, so they're pretty great. that is the end of my slides. Where I've gone for a while, but next week, whenever we can do it, I won't be able to present on Monday because I will have to come back home for a holiday, Yom Kippur, on Monday. But if you want to do this later sometime.
Yeah, we can skip a week or something.
So, or do it later in the week is fine too.
Yeah.
Like on Wednesday or something. Yeah,
But
that's
this
all I
was
have
awesome.
for today. Yeah.
You make these available, these slides?
Yeah, I can send them to you. Let me,
Okay, sounds good.
I'll just fix that one thing. But yeah, and I'll add more. I have to make a second pair for next week.
Mhm.
This is basically what I got done, and I thought it would be enough material. And it
No,
was,
it's a lot.
it's a lot.
lot,
So
yeah.
I was
I
trying,
want- yeah.
hopefully it's not too confusing. I'll send the slides. Let me just fix this one thing. Is there any questions or anything specific? Here it is. You want?
I mean, the stuff on filters is really timely because we're talking about points in the Badu group, and
Yeah.
I think they have a lot to do with that.
Mhm.
And then, yeah, no, I mean, it's great. I think knowing how the categorical stuff plays into
Mhm.
filters would really help. Like, I mean, I'm
Yeah.
assuming you're going to get to that point on the next.
That's the goal next time. Yeah.
Yeah.
A bit. Hopefully.
An unrelated question.
Yeah.
This is a nice software for presentation. What is it?
I'm literally doing this all on just on Keynote, just the Apple. I have a Mac. But I'm just adding all these equations with LaTeX. They have like an insert LaTeX formulas, which I don't think Microsoft has, or at least it didn't before.
Did you
They used
say
to make you like
Keynote?
click through things. Yeah, just Keynote.
Okay,
Yeah.
sounds good.
Just a minor
Okay.
question. At
Yep.
the very end, that third theorem that you
Mhm.
present on filters, is this somehow related to in calculus the squeeze theorem, or there isn't there a theorem that says like you can kind of take like the lower bound and I don't know. Yeah, it's
Yeah,
not
the squeeze
really
theorem, it
close.
has to do with like squeezing integrals, I think. It's like taking bounds. Oh yeah, it's when you can squeeze things between functions.
Yeah, something like that, right? It doesn't it
It's
only
been a long
work?
time since here.
Yeah, I wonder if that's.
Oh yeah, it has to do with limits of
True.
functions.
Yeah, like you have two different functions, and then they form like the boundaries
Yeah.
of some other function. It kind of has this
Yeah,
same
I don't
intuition
know.
as a filter, right? I don't know.
I don't know. There is a similarity. I would have to think about it to tell you for sure. Because if a filter is really like this sort of like upward directed things of a post set, like the easiest example of a filter, which is also an ultra filter, which we'll get to next week. That's where the real meat comes in. The simplest filter you can think of is just the set of all sets that contain a point, right? So if something contains a point or not, everything that's above it will contain it. If two things contain the point, obviously their intersection contains the point. So that's a filter, and it's an ultra filter because everything either does or doesn't contain the point.
It's like the largest filter possible, right?
Yeah, but the squeeze theorem, what it says is that if you have a function that's below one always, another function that's always below it, above it, if you have both of these below and above functions limit to the same thing, then the one in between limits to it.
I see. Yeah. Yeah, it's not exactly.
Can't think
this,
of off
but
the top of my head, but it's, yeah, I guess it's a similar intuition a little bit. Yeah, so next week I hope to, I guess, start with more things on filters and ultra filters, because there's a lot in this book. Most of the stuff I'm getting from this book, when I told you about the topology categorical approach. For anyone interested in this stuff, I would highly recommend it. It's pretty readable. as far as these kinds of things go. But yeah, that's where a lot of it's from. They have a lot of things with
Which one?
randomizing things to filters.
Topology.
It's called
category.
Topology, a categorical approach.
Yeah.
I have the Kindle version. Yeah, it just came out recently.
Right.
It's by Bradley Bryson and Turilla.
Yeah, that's a book Dennis and I are reading.
Oh yeah, yeah. It's quite good. I'm a fan.
Sounds good.
Yep. Any other questions or comments?
Yeah, no, I'll have to mull it over and ask you stuff next time or in between.
Of course. I'll send you guys this right now, actually. I'll just make a second one for next week.
Yeah, thank you so much, Yasha. It was really good.
Yep, you're welcome.
Clarified
Yeah,
a
this
lot
was
of
really
stuff.
good, man.
Yep.
Yeah, I had too many
Sounds
notes
good.
here.
Nice. Okay.
By the way, guys, what was I gonna say? Caron told me, I mean, he couldn't be here today, but he said he and Pedro, who also joined recently, I'm not sure if he came today. Yeah, he's here. Pedro, I'm not sure if you're there, but Caron told me you guys were thinking about trying to present like in a more organized way about Apolito's text, right?
Yeah.
Yeah. So the thing it was that I was talking to Caron about
Oh wait, let me.
about like some Mark Wilson stuff
Yeah,
that
go.
we're both working on, and then he suggested that we would do together. We're talking about physics avoidance, and then the idea is to sort of do something about this idea of like scale sensitivity or scale relative ontology that Mark Wilson does, and to sort of try to bridge that and scale anarchy. That's sort of the idea for now.
That's cool because he told me you guys were in between doing one presentation mixing Wilson and Apolito or doing two, right? Presenting the text and then presenting Mark Wilson.
Yeah, I think he mentioned that he talked about this with you, and then he said, and that you had the idea of doing it separately, and I think it's also good to do it separately, to do one and the other, because then I think mixing is not like it wouldn't like I mean like we wouldn't have enough time to mix them anyway.
Yeah, that's what I'm
Like
starting to see, that like we should be more conservative with how much fits into one meeting. I'm realizing it's
Exactly.
That's
That's
just why I
exactly.
remembered it. Yeah. No, but I find that such a good idea. I mean, I try to write down everything we already said we would like to do for the next meetings and so on. But I think we could try in the near future to organize a schedule for like what's going to be presented and when, so everyone can start like also organizing their time and. So,
yeah.
But we can talk this over through our joint chat window.
Sounds good.
Great, guys. I need to prepare some soup.
Sounds good. I have to move. I'm moving this Friday.
Oh, really? Already?
Oh wow.
So
Oh,
very
great.
soon. So it'll be a busy weekend.
Yeah, but it's a great news, man.
But yeah, if you guys want, I guess the second half either later next week or if you just want to skip a week, let me know. I could probably do later next week.
Yeah, because another thing we could do is if you want,
Or if you want to put something in between.
Yeah, we can like do. I think it would be a nice moment also to do like a recap meeting of everything we've done this far. Just talk it over. Also, there some people joined recently. We could be a bit more descriptive with what we've done. So.
Sure, that's a good idea.
So something a bit more loose.
Yeah, I like that too. Yeah, more informal meeting.
Yeah.
Yeah.
Okay. See you guys.
So the meeting is usually 5:30, 5:30?
Sorry?
Normally 5 or 5:30. Today was a little later.
Yeah, today we met a bit later than usual.
All right. Sounds good, guys.
Yep.
See you all.
Okay.
Take care.
Bye-bye.
Bye-bye.